Okay, so what we're going to talk about again, we're introducing the idea of covalent bonds today. I skipped your table.
Yes.
I'm sorry.
It's okay.
Thank you. All right, so we have been talking about ionic bonds. And ionic bonds is kind of like this third bullet point here, where ionic compounds result from an atom losing electrons, the other atom gaining those electrons, so they were transferred, and the forces that are holding them together are that positive and negative charge. The opposite charge is holding them together. Today we're going to be discussing covalent bonds, which is this guy here. So this is going to be where atoms are going to share their valence electrons in order to attain that noble gas configuration. The reason why they do it is the same as the reasons before. It makes them more stable because they're able to attain that noble gas configuration in the octet, the 8 valence electrons. So the reasoning is still the same. It's just a different way in which they go about it. So a covalent bond is going to be, again, the result of 2 atoms sharing their valence electrons. If 2 atoms are sharing electrons, they form what we call a molecule. A molecule is only as a result from sharing electrons. So a lot of times people use the term molecule incorrectly, and they like to use it for ionic compounds, but we use formula units for that. The other thing I want to highlight on this slide is that the molecule comes from 2 or more nonmetals. Nonmetals, so if we're looking on the periodic table, we have our staircase here, right? If I have 2 or more atoms on the same side, but also including hydrogen, hydrogen's also a nonmetal, that's going to be a covalent compound. If we have a metal and a nonmetal, that's when we know it's an ionic compound. So there are 7 elements on that periodic table that you need to be aware of that are called diatomic molecules. It means that these atoms, the elements themselves, the 7 elements that I mentioned, are going to be very unstable if they're by themselves. So that's why they always exist either paired up with another atom of the same element or just bonded to something else. The 7 elements that do this, there are 2 ways to remember it. This one is probably the one I mentioned the most. It's just looks like an assortment of letters, but it just phonetically you sound it out as being Brinkelhoff. That is not a real word. Again, I'm trying to give you mnemonic devices to help you remember this. But what Brinkelhoff stands for are the 7 elements. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. The other way that you can remember this is that there are 7 of these elements. They start at number 7 on the periodic table, and they are in the shape of a 7. So if you're looking at your periodic table, you place your finger on number 7, which is nitrogen. It's nitrogen, oxygen, fluorine. Then you go down to chlorine, bromine, iodine. It's shape of a 7. And then the last one is hydrogen, so it's up there. The things that you need to remember, I feel like it's hard for us to imagine what's happening here. But basically why these guys are important, and it's for almost every unit after this one we talk about, like diatomics will come up, is if I say hydrogen is reacting with oxygen and it produces water. You need to know immediately, because you've heard of diatomics before, that it's not just one hydrogen and one oxygen atom. It is hydrogen molecule, so 2 hydrogens bonded to one another, plus an oxygen molecule, which is O2, and then it's going to produce 2 waters at the end. Okay, so that's where there's context, is really we use it constantly in every unit after this. So This shows kind of what fluorine is. The reason why fluorine is really unstable, or any of those diatomics are, if it was just fluorine by itself, it has 7 valence electrons, and it is extremely unstable because it will do anything to get that last valence electron. So it never exists like this. It only exists in pairs out in nature. So there's 2 fluorine atoms that then are sharing a single pair of electrons in the center. And then that is what's making it diatomic, is because there are 2 atoms there bonded together. The other thing I want to point out on this screen is that this pair that is shared is either called a shared pair or a bonding pair of electrons. The electrons that are outside of this, that are not being shared, we call those lone pairs of electrons. So lone pairs are the valence electrons that are just not involved in bonding. Tomorrow we're going to start drawing Lewis structures. And when we draw a Lewis structure, we're showing 2 or more of these atoms that are bonded together, sharing their electrons. And the way that we do that is we draw a single line for every pair of electrons that are being shared between them. So 1 line is equal to 2 valence electrons. And if we draw only a single line, we call it a single covalent bond. The halogens group, since they have 7 valence electrons, they tend to form these single covalent bonds a lot. So when you have 2 atoms, they're being pulled together because the positive nucleus is attracted to the negative electron from another. So they're being pulled together. That first bond that forms between the 2, it happens first and in the center of those 2 molecules. That's called your sigma bond. And it's another word for saying it's the first single covalent bond that's formed. So the sigma bond forms initially between the 2 atoms in the very center. And then every bond after that is called a pi bond. Let me write this down really good. So in addition to just a single bond, though, you can have multiple bonds form between 2 atoms. You can have a double bond form, which means you're sharing 2 pairs of electrons, or that means you have 4 total electrons that are being shared there between them. Triple bonds form from 3 shared pairs of electrons. So we draw 3 lines. Each line represents 2 valence electrons. So that's 6 total electrons that are being shared between them. All right, so what is going to happen here? Again, like we said, our single covalent bond is called a sigma bond. That actually forms first between 2 atoms. If it then forms a double or a triple bond, each successive bond after that first one is called a pi bond. And it occurs from overlapping p orbitals. So we talked about p orbitals in the last unit. And if they overlap p orbitals, then you can form a double or a triple bond. So after you write this down, all you need to do is just look up at the screen for a second. So this sphere here, this is a carbon atom and a carbon atom, okay? And then there are 4 hydrogen atoms on the sides. The first bond that forms in the very center here, this is your sigma bond. Okay, so that's the first single covalent bond. The pi bond or the double bond is this overlap, but also this overlap. So one bond here, both of these make the second bond or the double bond. In the event that there was a triple bond here, it would actually come out of the paper towards you and then into the screen. Okay, so this, even though it looks like 3 lines, this is actually only a double bond there. Before I even change the screen, I want you to think about if I were to, like, just based on kind of what looks like here, all right, if we have a single, a double, or a triple bond, and I've kind of just written them here for you, right? This is an example of a single, a double, a triple. I want you to look at your neighbors. I want you to talk about 2 things. One, which one of these 3 are the atoms going to have to be closest together based on kind of what we've seen here? And then 2, how would that relate to how strong the bonds are between them? So see if you can predict, I'm using the word predict, which means I haven't taught you yet, but see if based on what we've talked about, single, double, or triple, which bond type are they the closest together, meaning the bond length or the length of the bond itself, is it the shortest or the closest together? And then 2, which one is the strongest? Okay, ready and go.
Yeah, I was just saying.
Right. Show me on one hand. So when I ask the question, in which bond type are the 2 atoms involved in the bond? In which bond type are the atoms closest together? Single, double, or triple? Okay, show me on one hand. Ready, go. Which one are they the closest together? All right, the correct answer for that one is the third one. Okay, so, and if you think about it, this is how I want you to like paint that picture for yourself, okay? This is just showing a double bond. If it was a single bond, there would only be that amount of overlap between the 2 carbon atoms. With the double bond, we now have this overlap in the center and then this overlap here. Overlap meaning literally their atoms have to overlap one another. For a triple bond, you add an additional overlap in this direction and that direction. So with that much overlap, it pulls the atoms closer and closer together. Does that make sense to you? It's kind of like if you want to share something with someone, you want to sit closer together with them because it makes your life easier. So the more materials you're sharing, the closer you are, it makes your life a little bit easier to share those things and have equal access. The other question I asked you is how is that going to affect the strength of the bonds? So which ones, now that we've established, and if you want to change your vote, now would be the time to do it, but which one do you think would be the strongest, the single, the double, or triple based on this? Meaning, which one are they held together tighter, I guess is what I would say. Vote, ready, 1, 2, or 3, show me on one hand. Show me, show me, show me. None of you are showing. The correct answer is 3 again, okay? So, if they're closer together, it's essentially we're thinking which one is the hardest to pull apart. With that much overlap, it makes the bonds really, really strong, and so we have to put way more energy into pulling them back apart. So on the next screen, it kind of summarizes that stuff that we just talked about in a nice little package. But the strength of the bond depends upon the distance between the 2 nuclei, and we call that bond length. As the bond length decreases, the strength of those bonds increase, meaning as they get closer together, it is a stronger bond. So singles like out here, then double, they have to pull in a little bit more, and then triple bond, they're right on top of each other, and therefore it's a stronger bond. Someone earlier told me like a good kind of comparison is like when you're breaking a pencil. So like a single bond, it's like a longer pencil than if you broke it in half. Then that's like your double bond when you'd have to apply more force to break it in half. And then when you have that triple bond, it's a really short pencil, and that's really hard to break, right? So that would be like your triple bond. The way that we define how like strong these bonds are with a term called bond dissociation energy. Bond dissociation energy means the energy I need to put into breaking the bond. So the stronger the bond, the more energy you have to put into breaking it. So this summary here just says the more bonds you have between two atoms, the closer the atoms are together, and therefore the stronger the bond is. So I think you have 3 more blanks on your paper. So that's you ordering single, double, triple in the order in which they're the weakest to the strongest. So we said the weakest is the single bond, the intermediate is double, and then triple would be the strongest bond. So that's what you're writing in those 3 blanks there. Oops, sorry. All right, the last thing that we're going to do is go over naming and formula writing, and then differentiate this from ionic compounds. So when we write the names of covalent bonds, some of the stuff remains the same. We're still going to keep the same name of the first element, the way that it appears. The second element in the name gets the IDE ending, just like we've been doing. But where it is different is that we're going to give prefixes based on how many atoms of each element we have. We also are not simplifying. So in ionic compounds, if you had like Mg4Cl8 is what you found out to be, you would simplify that down to MgCl2. But here we're not doing that. We just say the exact same number that matches the name. So the prefixes are in the table that are in your notes. The prefix for 1 is mono. The prefix for 2 is di. 3 is tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is nona. And 10 is deca. And a lot of those should look really familiar because they sound like shapes that you've seen, like a hexagon, like a pentagon, like a octagon or a decagon. All of those things are, they're similar, okay? So what we are going to do, the only kind of catch here, we're going to put the prefixes in front of those words, the element names. The second element, remember, still gets the IDE ending. If you only have, we only use the prefix mono for the second element though. If we only have one of the first element, so like here, I only have one of the first element listed in the compound, I am not going to use the prefix mono for the first element. I only use it for the second element. So that's why you see mono appear in the second one, okay? So for this first one, again, the first element we're just given, we just say the name. So this is going to be carbon. And then the second element, we add the IDE ending, and then we're also going to put the prefix for 2, which is di. So this is carbon dioxide, which all of you probably recognize, hopefully. The second one, again, we're not going to use the prefix mono for carbon. So I just say carbon here. Again, I just don't use it for the first element. The second one, though, I do use the prefix mono. So in this case, CO is carbon monoxide. And monoxide sounds really awkward, so we're going to drop the second O there and then just say monoxide. If you have I409, all right, and we're writing this one. What is the prefix for 4?
Tetra.
Tetra. So we're going to say tetraiodine. And then the prefix for 9 is nona, and it's going to be nonoxide. But when you have like an A and an O sitting side by side, like right here, I tend to drop the A. It just sounds awkward. All right, now if we do the opposite, where we're just writing the formulas, we just write down the element itself, and then the prefix tells us how many. So we have dinitrogen, so this is going to be N2. Monoxide is just 1 oxygen. So N2O is that formula. Phosphorus trichloride. This is just 1 because there is no prefix. Remember, we do that only for the first element. Phosphorus trichloride means there are 3 chlorines here. And then the last one is diiodine, which means there's 2 iodines. Heptaselenide. What element is selenide referring to? Selenium. Do you see that? Do you see SE number 34? Selenium. And then that hepta means 7. Yeah. So the hardest part of today's lesson is the next slide, or what I think the hardest part is for students. You have to be able to do 2 processes. When I give you any kind of compound name, you need to be able to look at that compound and tell if it is ionic or covalent, and then follow the appropriate naming system for it. So I'm going to first just erase. All right, so you have like a flow chart like this on your paper. It walks you through if it is an ionic or covalent bond. The first thing you should look for is there a metal in the compound? If there is a metal in the compound, then that means it's going to be, it's an ionic compound automatically. If it is ionic, that means that we need to balance out our charges when we write formulas. That means we're going to use the crisscross method. We might need to use Roman numerals to differentiate between transitional metals with more than 1 charge. We would need to simplify the formula to its lowest possible ratio between them. And we are not using prefixes here. If there is no metal, the other question before we just jump to covalent is there a polyatomic ion? And this is really talking about ammonium, because that could be a cation polyatomic ion. That would also bring us back to ionic. But if none of that is happening, then it's covalent. Remember, we said this is 2 nonmetals bonded together, but hydrogen is included in the nonmetals. If I see that it's covalent, I'm using prefixes, and I don't simplify the formula. So the first example here, we have Mg3N2. Is this ionic or covalent? It is ionic because magnesium is a metal. So that's like your sign, okay? So that means we follow the protocol for naming ionic compounds. We're just going to say the element's name for the first one, which is magnesium. So I just say magnesium. And then I don't have to really do anything else because magnesium is not a transitional metal. And then I just add the IDE suffix, so it's magnesium nitride. All right, C2H4, is that ionic or covalent? It is covalent because there is no metal. We have carbon and we have hydrogen, both of those are nonmetals. So this means I'm going to use prefixes. So since I have two carbons, then I'm going to say dicarbon. And then for hydrogens, I need to use that prefix tetra. So tetrahydride. NH4NO3. What do we think? Ionic or covalent? It is ionic because what's in there, it's not a metal, but it is a polyatomic ion. So since there's a polyatomic ion of ammonium, that's our cation, this is ionic. So I just say both of the polyatomic names. So this is going to be ammonium nitrate. All right, number 4, tricarbon octahydride. I see prefixes and I should immediately know that it is covalent. Good. So from here, all I have to do is just use the prefixes to write the formula. So C3H8. That's an 8, sorry. Looks weird. Well, no, it just looks German. Then we have chromium 3 chloride. Ionic or covalent? Ionic, good. I have a metal in that, so it's immediately ionic. Whenever I have ionic compounds and I write formulas, this is where we do crisscross. So I have Cr with a 3 plus, chlorine is a 1 minus. I crisscross my charges and I get CrCl3. And then our last example, we have dihydrogen dioxide. I see prefixes, so I immediately should know that it is covalent. So I have H2O2. Other things you should be aware of, some of these covalent compounds have common names because they were given names before we came up with this naming system. So water, we know is H2O, but it does have a scientific name of dihydrogen monoxide if we follow the naming system. Ammonia is NH3. Propane is that guy. This is hydrogen peroxide there, H2O2. So there are common names for these. They don't have to judge. But this is the naming system that we use. The other thing that we're going to